Okay, so in the previous lecture, we introduced the wave equation, and we, as well as so-called the stress energy tensor Q over here. This is the key for the vector field method, and its important property is it is divergence free, provided U is a solution to the wave equation. Using this, we derived the conservation of energy. The energy E will be a conserved quantity. And using this idea, we proved the existence and uniqueness for the Cauchy problem of a general wave operator P. So in this lecture, our focus is to study the long-time behavior of the solution. So first, let me set up the problem. Let U to be a solution to this Cauchy problem. Box U equals 0, U0x is a function. F and dtu0x is G. In other words, there's no source term. And here the box is the standard wave operator minus dt squared plus summation I goes from 0 to 1 xi squared. And what we want to achieve is to see that wave dissipates. In other words, this solution U should decay in time. So we want to get this type of decay estimate using the vector field method. That is, when we are going to to multiply Q with other vector fields, we use DDT that leads to the conservation of energy. And today we are going to introduce other vector fields, which eventually leads to the decay of U. And for simplicity, I'm going to assume the initial data, F and G, are both smooth and with compact support. Smooth with compact support, which implies, well, this U is also smooth, and for every fixed T, it also has compact support. Okay, so this is the setting, and we want to achieve the decay of U. Okay, on the left is our Cauchy problem, and we already know the energy is conserved. E, energy at time t2 equals the energy at time t1. And for energy, we are talking about the integration of du squared, which has the derivative of U in every direction, in the time direction and in the space directions. So it's great that we already have a conserved quantity. But one disadvantage of it is the lack of the base term, the base L2 term. So we are going to improve it. This can be done by the following lemma. Okay, before stating the lemma, let me introduce the notation. I'm going to use R as, well, the radial coordinate, x squared plus y squared plus z squared. And I'm going to use this as an abbreviation of 1 plus R to avoid this to be 0. Okay, so this lemma says, suppose we have a function on R3, be a function which R derivative of H is in L2. Furthermore, 1 over R times H is also in L2. Then you can use the L2 norm of DRH to bound the L2 norm of H over R. That's equal to some constant C times the L2 norm of DRH. And by the way, it's kind of tedious to write down the constant C at every single time. So we are going to use the following notation. Is less or equal to DRH. So this tilted inequality means the inequality holds up to some constant. Okay, so this is the notation we are going to adapt in the rest of the lectures. So this lemma is just about a function on R3. It has nothing to do with the wave equation. What it says is, well, we want to bound the L2 of H by the L2 of DRH. And the assumption that H over R is L2 is necessary, otherwise constant is a counterexample. So once we have this lemma 3, we can upgrade this E to include the base L2, define EB to be a half T equals T1 du squared plus R to the minus 2 U squared. Obviously, the EB energy is larger than the E energy. And this lemma 3 says, well, they are actually comparable. Together with the conservation of energy, we immediately get the following corollary. The EB energy at later time t is bounded by the initial energy. For any t greater to 0. Okay, now let's give a quick proof of lemma 3. The proof is pretty simple. It's based on the following simple inequality. A half h squared is bounded from above by r times h squared plus 2r squared times dh dr squared. This can be done simply by Cauchy-Schwarz. And we are going to use dV to stand for the area form of unit sphere. And we are going to integrate this inequality in R and along R and along the sphere. B dr. Then this term is going to give us, well, the L2 norm of DRH. This coefficient R squared times dV times dr gives the standard volume form of R3. And the thing on the left side becomes the L2 norm of R to the minus 1 H the assumption 1 over r times h is in L2 is used to deal with the remaining term. It is to use that, well, this term, after we integrate it in R, we pick up the boundary terms. The boundary near the infinity will actually decays to 0. And the boundary inside doesn't matter that much. And this finishes the proof. In particular, it says if H has compact support, we can use the L2 norm of the H to bound the L2 norm of H over R. And one advantage of including this base L2 norm is now we are able to bound the L infinity norm of the solution. So let omega to be omega 1, omega 2, omega 3. Those are 3 independent rotation killing vectors. Rotation. Killings. For example, omega 1 is phi. If we want, we can also write down the explicit form of omega 2 and omega 3. But the explicit form is not that important. What's important is, well, because they are killing vectors, they commute with the wave operator. Which means box U equals 0 implies box of omega U is also 0. We can apply the same energy estimate for omega IU. Okay, now the L infinity norm can be bounded through the following lemma. Still, this lemma is about functions on R3. Say we have a function h defined on R3. Then the absolute value of h is bounded by r to the -1. H squared is bounded by r to the -1 times the energy, the EB energy of h up to 2 angular derivatives. So this is not just the energy for h, but for we take the angular derivative of h up to 2 times. And we compute their energy, sum them up. It will be an upper bound of h itself. Then using this lemma, combining with corollary 4, we get the upper bound of the value of U by the initial energy in the following way. U squared is bounded by r to the -1 times the energy, not for U itself. Here we also need to commute with the angular killings at time 0. Okay, now let's prove this lemma 5. It is based on the Sobolev embedding. Let's fix R0 for 0 and R0 times h squared through Sobolev embedding along the sphere is bounded by integral S2 R0 times the angular derivative of h up to 2 times. This is because S2 is 2-dimensional and W22 can be embedded into L infinity. So this is Sobolev embedded. Then we need to bound this guy as 2 r naught times h squared. Well, let's throw away the angular derivatives. We can add them back at the very end. dv, remember dv is the area form of the unit sphere. So assume h has compact support, then we can take the r derivative of this quantity and integrate it from r naught to infinity. That leads to r naught to infinity, r is 2r dv of h squared plus r naught times 2 times drh times h. Okay, simply the fundamental theorem of calculus. And once we transform it back to the standard volume form of R3, we're going to find out that it is bounded by the EB energy of H. Then we can commute this inequality with omega up to 2 times. That finishes the proof of lemma 5. In conclusion, in these 2 steps, we improved the base energy E to include the we improved the energy E to include the L2 norm, and with that we are able to bound the L infinity of U in terms of these energies. But well, this is not decay at all. It is a boundedness estimate. To achieve the decay, we are going to introduce 2 other vector fields, 2 other currents. One is called the monoris current. The other is called the RP current. Okay, on the left is the setting, the Cauchy problem, and the stress energy tensor Q. Here we have the eta is the Minkowski metric, and the R3 part is expressed in the polar coordinate. They are squared plus the spherical coordinates. Here I'm going to use in XA and XB to denote theta and phi. And the idea of Morris current is actually pretty simple. We use ddt to achieve the energy estimate. Now let's try to use the radial vector field. That is, we multiply QAB with gradient R. Gradient R is nothing but ddr. And if we compute its divergence, it is QAB times the Hessian of R. And the Hessian of R is the second fundamental form of the sphere. So it has only angular directions. This becomes 1 over R times /U squared minus of R AB dAU dBU. Okay, this is some direct calculation. Here we use the notation /U squared to denote, well, du squared, but it has only the angular parts. Okay. So what we're going to do is we're going to pretend this term does not exist. We are going to pretend this term is 0. Well, of course, I will need to explain why we can do that, but for a moment, let's pretend that is the case. So in short, the divergence of this one form, this is called Morawitz current, is positive. It is 1 over r times angular derivative of u squared. Then let's apply the divergence theorem. Still between T2 and T1. In the bulk term, we are integrating something non-negative. On the boundary, this is T equals T1 to a B, gradient R times N minus the same quantity at T1 times slice. And once we compute this integrand, oh, by the way, N, let me remind you, are the normal vectors. Okay. So N is along the T direction. Gradient R, of course, is along the R direction. Their contraction with Q becomes dTu times dRu. This guy has no sign, but fortunately, it is already bounded by du squared, and whose integral is the energy we have controlled in the previous step. So using the Divergent Theorem, what we can get is the integral between T1 and T2 of 1 over R u squared is bounded by the energy at T1 and T2, which are bounded by the initial energy. Okay, so this is so-called integrated decay estimate. It means that, well, it does not directly tell you it decays, but it tells you the integral of some quantity is bounded. And T1 can, T2 can be anything positive. You can move T2 to infinity. That is still a bounded from above. Therefore, the integrand should decay. So this is okay, so I still need to explain to you why we can throw this red term away. This term is roughly 0 in the divergence sense. If we compute this divergence, h u squared minus gradient h times u squared, what we will get is twice h ab dau dbu plus twice h times u times box u minus box h times u squared. Some direct calculation. The first term is what we said could be viewed as 0. Here h is any function. And the second term is 0 if U is a solution. That is our case. And the last term is of lower order. It contains no derivative of U, just U itself squared. Therefore, this red box can be viewed as 0 because after adding certain divergence, it can be reduced to a lower order term, contains no derivative of U. Of course, in reality, one will still need to take care of this lower order term, and the final form of Morris current will be the following. Okay, so this is the form of the true Morris current. We times this Q multiply gradient R by some function H. And there are some lower order correction terms. The purpose is to take care of the zeroth order term. H and omega are explicit. And at the end, the divergence has this lower bound. We see this 1 over R, angular derivative of U squared, and there are two other good terms. Therefore, by applying the divergence theorem, just like what we did on the previous page, we get this integrated decay estimate. So this is Morris current. The next current we want to introduce is called RP current. And here, let me fix some notations. We use T as the time translation. Let's use L to be ddt plus dtr, and L bar to be dt minus ddr. L is the R outgoing null vector. L bar is the incoming null vector. This is T, this will be L, and this guy will be L bar. Both of these two are called null vector because using the Minkowski metric, their inner product with themselves are zeros. Okay, so the RP current takes the following form. RP minus 2 of QAB. But it's not the QAB of U, but the QAB of U bar times LB, where U bar is L. Sorry, U bar is R times U. Through a direct calculation, the divergence of this guy will be a half times R to the power P minus 3 times P dl U bar squared plus nabla slash U squared here. It has a coefficient 2 minus P. Okay, so, well, this could be computed directly. And this current was first introduced by Darfomos and Rarski. The way they found this current is by the following observation. Suppose U is a function of Tn R. In other words, it does not depend on the angular variables. It's just a function of t and r. Then box u equals 0 is equivalent to time derivative minus 2r derivative acting on u bar, that is r times u equals 0. In other words, u bar will solve a two-dimensional wave equation. And this one can be write as the L bar, the L. In particular, if we take the L bar derivative of dl u bar squared, this will be 0. After the integration, that corresponds to the RP current with P being 0. And we could insert R to the power minus P over here. This is P times R minus P minus 1. So this coefficient P appears over there. Okay, so this is the idea behind this RP current. Let's write that down explicitly. JP is defined to be RP minus 2 AB U bar times LB. And we want the divergence to be positive. So we want both P and 2 minus P to be non-negative. So we are going to apply this for P belongs to 0 to 2. Okay, so this in the above discussion, the divergence of this RP current is good. It is non-negative. What about the boundary terms? Okay. Again, through a direct calculation, if we contract the stress area tensor with L and T, this will be a half dl u squared plus a half angular derivative of u squared. In particular, it is non-negative. So it will have also a good contribution along the boundary. So this is the RP current. And the next thing we are going to do is we're going to combine RP, moral weights, and the thing we used to prove conservation of energy. Which is over here. On the top left, we listed the 3 currents we discussed so far. I'm going to call it T current. This Morowitz. And this is the RP current. Over here is their divergence. You will have the contribution in the bulk. The T current has 0 divergence, and the other 2, they will have non-negative divergence. Over here is what they are when they contracted with the normal vector with ddt. So we are going to add these 3 together. Define RP to be C Jt plus Jm plus epsilon times eta Jp, where C is a large constant, epsilon is a small constant, a small positive constant, and eta is a cutoff function. It is 1 when r is greater to 2. It is 0 when r is less or equal to 1. The reason to put cutoff there is, well, actually, this JP current is not smooth near r equals 0. It is singular. So one puts the cutoff there to avoid such singularity. And once we put the cutoff, the divergence will be a little bit off. There will be some error term, and that is absorbed by the Moritz current Jn. And finally, one put the T current Jt with a huge constant C to make sure the boundary term is positive. Then through the divergence theorem, one gets the following equality. T equals T1 J bar P dot with N plus, sorry, here should be T2, the later time, plus integral of omega BP. I'm going to use BP as the divergence of J bar P equals. Okay, so this is simply the divergence theorem. And let's see what these integrants are. J bar P dot N is the summation of terms over here. So that is comparable to du squared plus r to the power p minus 2 dl u bar squared plus blah slash u bar squared. Okay, so this is the boundary term. And the bulk is a summation of the thing in the yellow circle. So this is comparable to r cubed u squared plus p minus 3 dl u bar squared plus 2 minus p, the angular derivatives. Just copy everything. Okay, so this is what we get using both by combining the Moritz and the RP current together with the T current, which looks a bit complicated. But after this effort, we still cannot get decay. In particular, the boundary energy. The thing here, apparently, is non-active, but its integral will not be decaying. And the main reason is, well, it contains du squared. The integral of du squared is the energy E, and we know the E energy is conserved. It's just a constant. It will not decay to 0. This boundary term comes from the T current over here. Intuitively, what does it mean is, well, the energy is actually trapped between these two time slices. Therefore, we do not expect the energy to decay at the time slice T2. So the way to resolve it is to open a direction to let energy dissipate. Okay, so on the left is the J-bar current we constructed on the previous page. Now we are going to consider other to measure the energy along different hypersurfaces. Fix R naught positive. For tau greater to 0, we are going to consider the following hypersurface. This is the t-axis. This is R. And that's over here. So for R less equal to R naught, it is still t equals tau. But after that, we want it to move in the 45-degree direction. So this is t equals tau plus R naught minus R. So this is a piecewise smooth hypersurface. We'll denote this by sigma tau. The normal vector, so it has two parts. We'll denote this by part 1, this part 2. The normal vector of part 1 is ddt, just like we have used so far. And the normal vector for the part 2 is, it looks funny. Because part 2 is a null hypersurface. So its normal vector is tangent to it. Its normal vector is L. So this is the hypersurface on which we are going to measure the energy. Just to check quickly, well, what would be the JT A dot L? This will be a half dLu squared plus a half angular derivative of U squared. Compared to the thing before, we can see the L bar U is missing. So the thing on the right is less than the thing on the left. Okay, so this is sigma tau. Then we time translate it, sigma tau prime. We denote the region in between by d tau prime. So again, apply the divergence theorem in this region. What we get is integral along sigma tau prime, j bar p dot n plus d tau 1 to tau 2 bp, which is the divergence of j bar p, equals the boundary term at the previous time. And here, j bar p dot n, well, now it has two pieces. On piece 1, that will be comparable to du squared and on the second part, it is a null hypersurface. It will be comparable to du squared plus angular derivative of u squared plus RP minus 2 L U bar squared on the second part. So let's define the integral of this guy to be EP tau 1, EP tau is the integral along sigma tau. Then the divergence theorem will tell us for any p belongs to 0 to 2, in p, when p is in this range, bp will be positive. Then we have EP tau 2 is less or equal to EP tau 1. Okay. So this comes from these two terms. Moreover, if p lies between 1 and 2, then actually the integral from tau 1 to tau 2, EP minus 1 tau, d tau will be bounded by EP tau 1. This comes from this bulk integral. After writing down what BP is and carefully check, one can see it is comparable to EP minus 1. So from the, now we have two inequalities. From the double star, we can see, well, EP will be bounded for any p. In particular, E2 will be bounded. In the triple star, we see, well, the integral of E1 is bounded by E2. Therefore, E1 tau will be basically like tau to the minus 1 times E2 tau. And you can iterate this procedure to get EP tau will be bounded by tau to the minus 2 plus p times, sorry, here's not, the initial E2 energy. And this is where we see the decay of the energy. We combined three different currents, JT, JM, and JP. And we measure the energy not on the horizontal time slices, but on these piecewise smooth hypersurfaces. At part 1, it is space-like, and our part 2, it becomes null. The reason here we see the energy decays is, well, this opens a direction where the energy can dissipate. Okay, let me summarize what we have discussed so far in a single theorem. So in this theorem 7, is to summarize what we have discussed so far. We have initial data, F and G, which are smooth with compact support. U is the solution to the Cauchy problem. And we we define this number, it is E star, which is computed at t equals 0 slice. This guy, if we want, we can rewrite it in terms of f and g. Then we define the EP energy like this. It has two pieces. At piece 1, it is the integral of the u squared. At piece 2, it's a bit more complicated. But upshot is, well, for p belongs to 0 to 2, EP tau will decay like tau to the -2 plus p times E star. And using this, we immediately get, we can also bound the subnorm of U. That is, U is bounded by U is bounded. U squared is bounded by R to the -1, tau to the -2 times E star. So compare to corollary 6, which was E star, sorry, this is A star with U up to 2 angular derivatives. Corollary 2, we have the U is bounded by -1 times so the proof is almost identical. The only difference is now we know the energy EP will be decay. If we put t equals 0, it decays like 1 over tau squared. That's the reason we have a factor tau squared over here. So this guy says wave dissipates. Okay, so this is how we can use the vector field method to prove the solution to wave equation will decay in the Minkowski spacetime. And unfortunately, we don't really have time to go into the structural spacetime. So let me just list it who achieved such a decay. In the structural spacetime that was done by Darfomos and Ronowski, also through this vector field method. Actually, this RP current was invented by by Darfomos and Ronowski for in the structural spacetime. And here I adapted their method also to Minkowski spacetime. And later, this method was pushed even further to the Kerr spacetime. Each time there are several issues needs to be resolved by choosing, by carefully choosing the vectors. But the upshot is, well, one can use this idea. The stress energy tensor is divergence free to get pretty far. And this is for linear wave equations. So that this is for this lecture. And in the next lecture, we are going to discuss semi-linear wave equations still using this vector field method.